Hello everybody. Today we're going to be going over an Arduino based tachometer utilizing a brushless motor as the device we'll be measuring. In this video we will be going over the problem and the requirements, and then as well as the design, the code, the results, and the actual implementation. So starting with the problem that we're hoping to solve is that through implementing a IR LED and a photo transistor, can we measure the RPMs of a brushless motor that is controlled through an ESC, specifically the Q-in out 30 amp 4S2. So the requirements that we're going to be addressing are developing in a language executable on an Arduino, executing code on an Arduino, utilizing either a round robin with interrupt or function queue design. We will be utilizing the round robin with interrupts. Transmit the RPM readings via CSV file format, transmit the readings via serial, utilize an IR emitter and detector, utilize a brushless motor with a propeller, and then create a chart of this with the RPMs over time. So beginning with our software design, we have our start. This goes into our setup, which contains instructions for starting our serial, setting the IR pins as input pull-up. This will be grounded, and that will actually kind of implement the interrupt. We then attach our interrupt to that IR pin. We set the LED pin as output. We create our servo object and attach the associated pin to drive that servo object. We set that servo speed to 0, and then we create a previous time variable and set it to current. This will be utilized in the main loop for handling some time-sensitive operations. In our main loop, we have 4 main sections, the first one being serial. So we check if serial is available, so it has a user inputted serial. And then if it is, we get that value, and then we really check, is it equal to exit? If so, yes, exit. If not, is it equal to values? If it is, print that CSV data object, and then continue on. Next, we have our interrupt boolean. This really is just kind of a nicety. So we set the LED to off, and then we set interrupt boolean to false. This set of if statements is really just utilized for allowing a user to debug the program and see if the interrupt occurred. We set the LED as on, and this turns that off. Next, we have a kind of a time controlled if statement. So we get the current time, we minus that by the previous time, and then we check if that difference is greater than our RPM interval time. So right now we are utilizing every second we calculate the RPMs, which is based off the revolutions or interrupts that have occurred since the last time we've calculated them. So we take that, we save that RPMs to the CSV file in the millis, RPM format. We set the revolution to 0, and then we set previous time is equal to current time. Lastly, if it is the first run in the loop, we wait 3 seconds and we start the servo incrementally with speeds from 0 to 1, which are then utilizing a map command to actually write the angles to the servo object. Our interrupt is pretty simple. It's on the phototransistor grounding, so when the IR is not available, then we actually set the revolutions or increment the revolutions, and then set the LED to low, which turns it on, and then we set the interrupt boolean to true. Next, we're going to be going over the actual code for this implementation. So we have our header files, which are just the arduino.h and servo.h. We then have our interrupt boolean, which was discussed earlier as just kind of a nicety to show that interrupts are occurring. We then have our pins, so we have our IR pin, our photo pin, our servo pin, and our LED pin. Under the servo pin, we have our servo object, and then just some variables for handling the timing, and then also for handling that first loop, and then our revolutions and RPMs. Next, we have our CSV data object, which is just millis, RPMs, and then a new line character. And then we go into our 2 functions. First is that set speed, which really just handles mapping the speed to a angle, and we write that angle to the actual servo. Next is the photo ISR interrupt. We increment the revolutions, and then we write that LED pin to turn it on, and then we set our interrupt boolean to true. Next, we have our setup where we start our serial, we attach our pin and attach the interrupt to that pin, and then we have our pins for the IR emitter, so we set that to high, set it as output and set it to high, and then we do the same thing for the LED pin. We set the output, and then we set it to high, which is off. And then we have our servo, so we attach our servo pin to our servo object. We set the speed at 0, and then we set our previous time to milliseconds current. And then we print out some helper functions. Next, we have our main loop. We can see we have our serial that was discussed in the design. So if it's equal to stop, we exit the application, and then if it's equal to values, we print out over serial the CSV data. We then have our interrupt boolean if statement, so we write it to high to turn it off, and then we reset our interrupt boolean. Next, we have our RPM calculations that append the CSV data, so we can see we print out the revolutions, we print out the time difference, and then we calculate the RPMs based off a minute divided by that time difference times our revolutions. So even if this is slightly over or under 1,000, the actual RPMs will be based off 1,000 milliseconds. We then print those RPMs out, and then we update the CSV data object. Lastly, if it's the first run, we set our servo speed, so we delay by 3 seconds just to allow some time before it ramps up, and then we set it by looping through from 0 to 2, which then just gets mapped to angle from 0 to 180, and we set the servo speed there incrementally with a delay.
Hello everybody, this is the overview of the actual physical components and the design for the tachometer. Starting with the board and the photo transistor, we can see we have an LED or an IR LED and then a photo transistor. This is connected to pins D1 on the IR side, and then the photo transistor is connected to D5. These are handling the actual simulated button press or sensing throughout the process. And then for our brushless motor, we have that connected on D6, and then it is also grounded onto the ESP8266 as well, right there. This goes to the Q-Win out ESC, so we have our pin out, which is that D6 pin, and then we have that grounding going to the ESC. The actual pin out is handling the provided power. This is our ESC connection. We can see that we have a live wire and then our grounding. That goes to this board, which then gets hooked up to a LiPo battery over here with this connection. So that's handled there. With regards to the servo, we just have 3 connectors here. We get wired to the servo, and that's put on a wood plank to keep it stable.
So on the top we can see that we have our actual serial output, and on the bottom we have our motor. We can see that in the top we've just restarted it. We're getting some output. The servo has started up, and we're getting some RPM readings. It is important to note that these RPM readings aren't the best, as will be explained in the actual code overview or code results. So now that we have the test run, we can actually output the results. These results are taken from a different run, but the functionality remains the same. So we have a Jupyter notebook here, and we actually have a CSV file with the millers and the RPM saved in there. So we start off by just importing our libraries. We're using matplotlib, but everything else is a standard library. We create our environment variables, so our file path for that data, and then our CSV data, which is just an empty string. Previously, we were requesting data over async. That's not utilized anymore. We're just writing out to serial, so we open that file. We then convert it to 2 lists. One is that milliseconds list, the other is the RPMs, which will be used for graphing, and then we actually plot that. So we can see here we have a spike up high, and then it kind of levels out. It is important to see that, like, because we were holding the emitter by hand, we can see we have a lot of spikes here. I imagine that if we had an actual physical construct, it would be more normalized. So that is the overview of creating our tachometer with a IR emitter and detector and utilizing a brushless motor for creating the interrupts for that.